Welcome everyone to our introductory lecture on autonomous systems, which is part of the series of lectures within the project Autonomian, which is Erasmus Plus funded project, a digital package for autonomous systems and self-driving vehicles. The project is led by ITT Group from Estonia. The partners are Viljandi Professional Education Center, Silesian University of Technology, Riga Technical University, and Riga Technical School. My name is Agris Nikitenko, and I'm representing Riga Technical University. Today we're going to discuss introductory topics on autonomous systems, safety and ethics related to autonomy. In its essence, autonomy is one's ability to make a decision on its own. In the context of technical systems, we refer to systems' ability to generate an alternatives of possible decisions, to select one decision, possibly the optimal one or the most wanted one, and to implement it as a sequence of actions. Within the context of autonomous systems, usually they are classified by the application domain. In our course, we're referring to the following application domains and following autonomous systems by their application: autonomous cars, unmanned ground vehicles, unmanned aerial vehicles, and unmanned water and underwater vehicles or vessels. First of all, let's discuss autonomous cars, which possibly are among the most anticipated technology currently being developed. Self-driving cars in their essence or tracks usually are those which are not piloted by a human driver, which means they possess a possibility to make decisions while the car is driving without involvement of the human operator or the driver. It usually combines dedicated software, dedicated sensor systems, and control decision-making mechanisms. The main data processing steps, which is a crucial set of steps to achieve a certain level of autonomy, are the following. First of all, mapping, which is among the most fundamental abilities of autonomous cars or autonomous vehicles in general. So its ability to build a model of a surrounding environment where actually will be decisions made and where the future actions of a car will be modeled. The next, since the cars are heavy vehicles, they are related to potential dangerous situations to surroundings, including pedestrians, including other cars, or static objects like traffic lights, like traffic signs, and other objects. So the data should be processed in real time, which means it's a general ability of a vehicle to generate a decision within a certain limited time interval. The next ability, which is related to future forecast of future states of the environment, is modeling. So once the mapping is done, the car is capable of modeling of future states of the environment using the map, or which is a fundamental model of the environment. Decision making as such is ability to both to generate decision alternatives or alternatives of sequences of actions, and to pick one which is the most desired, the most wanted, the needed, or the optimal one, depending on particular decision making mechanism. And as the last one is ability to execute the actions as a result of decision making. Environmental footprint which is another consequence of heavy use of autonomous cars, which might be shifted both to increased footprint due to the increased mobility or decreased footprint due to use of smart grids, energy grids, or shared car services. Unmanned ground vehicles. Generally, we refer to unmanned ground vehicles as autonomous mobile robotic systems. Their typical applications are military operations, which are related to potential harm for human health, logistics, which are potentially related to monotonic work done by autonomous robotic systems, like delivery goods within a certain territory or within a certain area. Industrial cleaning, which potentially could increase both cleaning quality and decreased monotonous work for human operators. And agriculture, horticulture, where again we could use mobile robotic systems to increase both productivity and quality. Unmanned water or underwater vehicles or vessels. Usually we associate them with typical applications like military, including security, patrol and combat vehicles, and commercial, which are ferry cargo delivery ships, even on intercontinental scale or locally within the shallow waters. Autonomy. Autonomy as a phenomenon is very complex as a concept. We're going to discuss a few of most significant aspects of autonomy as such. Due to many reasons, we need to measure the level of autonomy and to quantify it. And the reasons are the following. First of all, depending on autonomy level, system owner might expect a certain performance or functionality. So it's related to the functionality and market potential and expectations of owner of the system or operator of the system. Like we expect in a certain way, our car is responding to our control inputs. Due to different system applications, regulations might be different, and the same applies to the different levels of autonomy. One regulations might be different for fully controlled systems, remotely controlled systems, human operated systems, partly autonomous systems, and fully autonomous systems, which is related both to security, functionality, and safety in a wider sense of those words. Sometimes it is necessary to forecast the potential performance of autonomous systems due to modeling reasons, due to design reasons. And that is where measurement or assessment of autonomous operation potential is very, very necessary. There are several earlier attempts to describe or quantify autonomy. First of all, a model ALPHUS, which provides a framework for combining tests and metrics to assess autonomy of an existing system. So going through a series of tests, we can quantify the level of autonomy and operation performance during those tests, and that's how we assess the overall level of autonomy, overall level of performance under certain autonomy. NCAP, which is non-contextual autonomy potential, provides a predictive autonomy measure relying on tests before actual system is used. So it means we can examine both the system design, the system complexity, and then we can provide those measurements as an input and to assess the autonomy before actually the system is being applied. And the last one is mission performance potential, which differs by the following assumptions. The first assumption is not necessarily performance increases gradually if autonomy level increases as well. There are lots of examples where increased autonomy causes a drop of overall performance within a certain mission. So performance of the same unmanned system can vary from mission to mission. So it means the performance itself under a certain autonomy level is depending on particular mission where the system is applied. There are several organizations which provide different levels of autonomy. The first is CAE, which provides autonomy levels for self-driving cars or autonomous cars. There are 6 levels. There is a level 0, which means the overall operation is human operated. So it means human driver is watching over the full operation mode of the vehicle, while level 5, which is the most autonomous one, where the system actually provides a full autonomy and a driver is not needed at all, and driver is more like a passenger. Depending on particular level, there are a split of functions which are performed by the driver and which are performed by the autonomous vehicle itself. In the drones world, there is a different scaling. However, there are also 6 autonomy levels, which also starts with no autonomy, which means the vehicle itself is being driven or controlled by using some remote control units in a distance by the pilot or by the operator. While the full autonomous modes means that all the operation, during the whole operation time, system is making decisions on its own, and the drone is fully autonomous, requiring a zero attention from human operator. Safety. Unfortunately, currently none of autonomous technology is ready for a wide acceptance, and mainly due to some safety issues, safety challenges, and sometimes safety acceptance by the public. First of all, why safety is needed and what are the most anticipated aspects of safety tackled in near future and being tackled currently. There is a specialist group which is called Autonomous Systems Working Group, SASWG. So that has identified the most significant safety challenges considering the following aspects. The first of all, domain-specific expert opinions on high-level issues within the domain, which means that within certain domains of application, like logistics, for instance, or military operations, specialists have not agreed on safety procedures, have not agreed on safety regulations or safety issues, which slows down technology development and technology acceptance. The next aspect is a set of modeled examples within a certain domain for systems and their possible use cases, which again might differ from one application domain to another application domain. And since we do not have a template-based or template examples, it is hard to do any globally accepted safety tests. Analysis of control system is another issue, since we need to agree on procedures, safety procedures or test procedures to issue certificates and allow autonomous system to participate in general traffic. The next aspect is analysis of experienced accident. which means that the group needs to agree on certain previously experienced accidents that might be template accidents where autonomous control systems might be tested in. Otherwise, if the agreement is not achieved, again we go back to template modeled environment use cases and template test procedures which are necessary to allow those systems to participate in general traffic. The general consequence, which the group safety and autonomous systems working groups have came up with, is related to both safety procedures, test templates, and modeled environments which are relevant within application domain only. Each domain, application domain of autonomous system has its own safety challenges. First of all, air, which is among the most heavily regulated domains. Unfortunately, the current regulation is too heavy for autonomous systems, and it really slows down the overall development. And the current experience is not directly transferable to autonomous systems, where human in the loop is in a very, very limited amount, while in the existing regulation, human in the loop is heavily part of the essential part of the whole safety procedure spectrum. Therefore, very challenging is interface and communication to air traffic control systems. Currently, air traffic is monitored and controlled by humans. Unfortunately, autonomous systems cannot communicate in the same way as human pilots, and that's why the communication itself with control centers is very, very challenging, both for controllers and for the system developers. Third-party risks, which are related to software updates, protocol updates, inconsistencies of the software, and so on and so forth. Due to those software updates, there might be there is a risk of appearing new software bugs or inconsistencies, which might lead to safety compromising. Reliance of external systems. In autonomous systems, there is a heavy reliance on overall infrastructure, including GNSS systems, global positioning systems, including the different beaconing systems, vehicle-to-vehicle communication protocols, and communication itself, communication channels, which might be part of the of external environment, external infrastructure, and in case of malfunctioning of any part of this environment, might lead to compromising the safety and might lead to some safety risks. Removal of human senses, which is related to vehicle health monitoring. Human operator being part of the vehicle itself during the flight, for instance. Human operator feels, or human pilot feels, in generally it feels the behavior of the piloted vehicle. Unfortunately, in autonomous systems domain, this field is removed, and it means the only thing that remains is sensor systems. And in case of sensor system malfunctioning, unfortunately, no data comes to the human operator, and that's where the health monitoring is lost, which creates potentially safety risks. In autonomous driving domains, there are a little bit different risks, safety issues. First of all, assuring driver readiness. Due to different modes of autonomy where autonomous car may operate in, Switching between or among those different modes means the driver needs to be ready to take over control under different situations and under different autonomy modes, which means that it actually requires a constant level of readiness of the human driver to be involved in the control loop. Unfortunately, it is not always possible, since human driver not always is aware of current autonomy mode, and it means going to another autonomy mode means going to another different behavior of an involvement of human driver, which is very challenging. So if we constantly require being ready to be involved in the control loop, it means human operator actually participates in the driving of the vehicle throughout the time of driving. So the autonomy itself is lost, and attractiveness of those technologies is lost. Connectivity with other vehicles. So there might be a necessity to communicate with other vehicles for traffic safety and traffic control reasons. There might be different communication modes that need to be switched seamlessly, including the overall communication channels that shouldn't be lost at any time of operation, which is very challenging and might be related with safety issues. Through live behavior monitoring, which means that as I was stating previously, autonomous cars are heavily equipped with different sensors, which collect data not only from the environment but also of the operator itself, which means throughout the use or lifetime of the vehicle, the data should be handled properly, which means both volume and safety. Behavior updates. Behavior is related both to driver and the autonomous vehicle itself. Driver is used to operate the vehicle in a certain way, and due to software updates, the behavior might be changing, and it means the driver has to be not only notified of the changes but also trained to handle the car properly due to those changes. There are certainly questions which are open questions. How to balance the existing behavior in terms of should we prefer short-term behavior updates over the long-term or long-term behavior updates, or should we prefer the self-acquired experience and self-acquired behavior in a cooperation with the driver, or cloud provided, which means a collective behavior, which is sort of average behavior. So those questions are open, and we do not have answer at this time. Value of simulations. Sometimes simulated environments are over-optimized for certain scenarios, and the scenarios themselves are over-optimized or so-called cleaned. It means while we are training the autonomous control systems, those over-optimized scenarios become part of the behavior of the system itself, which might be too far from the reality. How to assess the distance from reality is an open question. Safety in the defense and maritime domains. Besides the all mentioned, there are certain additional challenges. In the defense, there is always a bias between mission completion and safety. So there might be conflicting goals or conflicting requirements for completing the mission, which might lead to the destruction of the system itself and the safety. So it needs to be assessed which of those goals, which of those biased consequences are with the highest priority for a certain mission, for a certain situation, for a certain level of autonomy, which is also an open and very challenging question. Technology acceptance, since the military domain and defense domain itself is related to potential loss of human lives, technology acceptance and reliance of technology is essential and crucial. Currently, the question how to increase technology acceptance among the personnel, military or defense personnel, is an open question. In the maritime domain, there are certainly some additional challenges. First of all, long communication paths, which are limited due to distance from the coastline where ships are traveling, autonomous ships are traveling, and it means there is a limitation to the bandwidth which might be accessible by or used by the autonomous ship. It means overall real-time monitoring might be not possible for a certain use case. The same applies for the monitoring infrastructure. Sometimes it is not possible, and most of the times it is not possible to monitor the autonomous device or the autonomous vessel during the whole traveling over some certain path. So it means, again, we need to rely on autonomous control systems mostly of the time during the operation. Weather conditions, which in maritime domain are very, very challenging, and unfortunately they might be unexpected and very hard to predict, which leads to unpredicted or unpredictable conditions under which the system should be controlled. And at last, hostile adversaries, which is part of the maritime domain experience, even a recent experience during the last few decades, which is still an open question, and it's very hard to ensure proper control over device, over a vessel during those adversaries. The next topic, which we will cover as an introduction here, is ethics related to autonomous systems. Why ethics are important? So, first of all, we develop technology faster than we can understand the implications of technology application in masses. So it means there are certain implications, both due to different reasons, that we cannot forecast, and we cannot forecast changes in our society due to introduction of autonomous systems. To interpret applications according to the current social and moral frameworks, which for certain time might seem to be static. However, involving things like artificial intelligence, heavy data processing, and autonomy as a phenomena might change it dramatically. Unfortunately, it's very hard to anticipate what are those changes. We also develop technology faster than we develop and implement legislation and policies, both global and national. Currently, there are technologies ready for autonomous operation for some certain use cases in certain domains, while legislation and policies are not there yet. The main questions within autonomy that probably might arise, and which are very obvious to people, to us, to autonomous system users, are probably the following, which are usually called as social dilemmas. In the context of autonomous car, we might imagine that there is a situation where a car accident is inevitable. So it means someone will die probably, and we need to decide, or the system needs to decide, who lives and who dies. And as researchers are pointing out, due to as a result of a rather long experiment, social experiment, the question or the answer on this question is different in different nations, in different continents, in different countries. So it means the control systems might be needed to be tailored for particular, not only use case, but also for particular region. In the military context, saving lives not always is a part of the mission. So some smart weapon systems are built for killing people, not for saving them. However, sometimes it is necessary to change our plans or to change the goals or targets of the smart weapon to save lives of civilians, which is not part of the imperative of the weapon systems as such. And at last, in the context of people intimacy, how close is too close? So there are lots of systems that might be used in a close interaction with humans due to different reasons. And lots of data is as a result, lots of data is processed and collected. And that's where social dilemma becomes very urgent. Sometimes those systems are remotely controlled or partly controlled by human operators. And then the question how close the system should come or should go or to particular patient or particular user is an open question. Unfortunately, I don't have an answer, and this is something that we need to explore during the next years. Thank you for your attention. That was an introductory lecture just to show up the questions that are covered within our course, within our course book. Please follow to our links to our webpage of the project, and you can access all the materials available there.